My guest today is Rob Louw.
Today, I'm going to be talking about the greenhouse effect. Just briefly, my name is Rob Louw. I graduated as a chemical engineer some many years ago and went on to do a master's degree in engineering after that. I've worked most of my career in the chemical industry, but after retirement, I took up lecturing in physics, which has always been a favorite subject of mine. And just recently, I've got hugely more interested in what's going on with greenhouse gases and that. And what I found was that search as best I could not find anything that really explained what the greenhouse effect was and how much changes to greenhouse gases might have on the planet. So I've gone and researched it as a senior researcher, senior in years, and I'm hoping that I can put across a story which people can understand. This lecture you see, I've been delivering to U3A organizations in the UK and in South Africa, and I've also lectured at the summer school at the University of Cape Town. So let's get started and have a look at this, and hopefully I can get people to understand it. And I'm going to make an offer up front. If there are any schools or U3A institutions in the UK or even the USA, which I frequently visit, I'm quite willing to go anywhere to share this with anybody who's interested. And I'm going to keep it simple, and I'm going to follow what Einstein said at his 1933 Herbert Spencer lecture. And his statement was, everything should be made as simple as possible, but not simpler. I sincerely hope I achieve this objective. I don't want to oversimplify things, but neither do I want to overcomplicate things. Earth's climate, as most of us know, is strongly influenced by the balance between incoming solar and outgoing heat radiation. Now, in this process, greenhouse gases absorb and re-emit heat, changing the rate at which heat escapes to space. And this is the key. It's the rate at which heat's escaping to space that determines just how big the greenhouse effect might be. In my presentation, I'm going to explain how, without maths, greenhouse gases, especially carbon dioxide, affect Earth's energy balance. I say especially carbon dioxide because that's where most attention is. But in fact, water vapor is the the most important greenhouse gas that we have. And I'd like to just add a point. Carbon dioxide is often wrongly labeled as a pollutant, but it is in fact the gas of life. And I have another similar lecture that I've put together on photosynthesis, which I'm willing to offer as well, where I do explain why carbon dioxide is such an incredible compound. Okay, let's get stuck into a bit of the physics, and we'll start off by looking at the Earth's atmospheric composition by volume. You'll notice straight away that oxygen, nitrogen, and argon make up almost all of the atmosphere. There are a small amount of inert gases, which add up to, fractions of a percent. And then you've got the greenhouse gases. And you'll see there that carbon dioxide literally only makes up 0.04% of the atmosphere. Methane makes up even 0.302% or 2 parts per million of the atmosphere. And then there are a few other trace greenhouse gases such as ozone, nitrogen, nitrous oxide, etc., that add up to another tiny amounts. There are other small quantities of gases in the atmosphere in addition to above, but I think the key takeaway point here is that in dry air, carbon dioxide only makes up 0.04% of the atmosphere. The main gas gases, including water vapor, forming the Earth's atmosphere look like this pie chart that I've shown below. You can see there nitrogen is the dominant gas at about 78%. Then you've got oxygen, you've got a tiny sliver of inert gases, and then you've got a slightly bigger sliver than I showed before with greenhouse gases. And the reason for the difference is I've added the Earth's water vapor into the green slice. Now, the problem with water vapor is there isn't one number that represents the Earth. It varies between 0 and 4%, 0% at the poles, and roughly 4% somewhere near the equatorial regions. But on average, one could talk about 2%. But just bear in mind that it is very variable. And again, you can see if you look at the blue bar and the red bar, which represents carbon dioxide, you can see water vapor in quantity terms is way more than carbon dioxide is. So it's not surprising that as a greenhouse gas, it is a very important one. All right, let's have a look at the Earth's atmospheric temperature profile. I appreciate that this will come as something new to a lot of the viewers, but it's interesting to note that at the surface of the Earth, the air temperature is about 15 degrees centigrade. And the first layer of the atmosphere is called the troposphere. And it stretches up to an altitude just a bit higher than Mount Everest. It's about it stretches to about 11 or 12 kilometers above the surface. But one has to remember that this changes. It's more at the troposphere has a higher altitude in the tropics and a lower altitude near the poles. But the key point here is that as you rise vertically through the troposphere, there's a linear decrease in atmospheric temperature. And this, of course, does affect how effectively Earth's heat radiates to space. If you radiate from a high temperature near the surface of the Earth, you'll get lots of radiation. If you radiate from the top of the troposphere where temperatures are a lot colder, the heat flux starts to drop because the temperature is reducing. But then there's an important part which is not always common knowledge, and that is that the layer above the troposphere, which is called the stratosphere, which is where our ozone layer is, the temperatures initially stop rising, they remain static, but then they start to increase right up to the top of the stratosphere, which is at something like 48 or 50 kilometers above the Earth's surface. So a gas that's radiating to space in the stratosphere will radiate more intensely the higher up in the stratosphere it is, because there it's warmer. Something that is quite important to understand when we look at the role that greenhouse gases play in keeping the planet at the temperature that it is. Okay. The concentration of the key greenhouse gases, carbon dioxide and water vapor, are shown on this chart. Now, what you will notice that carbon dioxide at about 0.04% in the atmosphere starts at that level at the ground, and all the way up through, right up to the top of the stratosphere, the concentration is constant. And the reason is that carbon dioxide, A, it mixes very well, and B, it doesn't go through any phase change. It remains a gas at those temperatures. It doesn't freeze, so it doesn't change from a gas to a liquid or to a solid. It's a gas all the way up. However, with water vapor, that obviously starts at a much higher concentration near the ground, somewhere between 0 and 4%. Rapidly, the concentration of water vapor as you go up through the atmosphere rapidly decreases. And the reason for this is that as soon as you start traveling up through the troposphere, the troposphere, the water first cools down and it reaches its dew point. When it reaches its dew point, the water starts to get to condense and form clouds. If it then rises to a higher altitude, you get to a point where the temperatures are at 0 degrees centigrade or 273 degrees Kelvin. And at that point, water freezes. And then its concentration drops very, very sharply because the vapor pressure of ice is much, much lower than the vapor pressure of water. So you get that rapid. So water behaves very differently throughout. The water vapor behaves differently in the atmosphere to carbon dioxide. Carbon dioxide's concentration is constant, but water vapor's concentration decreases with altitude. Here I've drawn up the Earth's radiation balance. And what we have is that all the heat that the Earth receives comes from the sun. And it comes in the form of incoming shortwave solar radiation, which I've shown as those yellow arrows on the left of the diagram. Now, the width of each arrow bar indicates the relative quantities that are doing the different things that I show in this diagram. So if you look what's incoming from the sun, you've got shortwave radiation, some of which is absorbed by clouds, and that's illustrated by this narrow arrow here. Then you've got some more radiation, which is some of which is absorbed by the atmosphere itself, and that's depicted by the width of this arrow here. And then the really big arrow depicts how much of the sun's heat actually reaches the ground and gets absorbed by the ground. And that shortwave radiation, those first three bars, equate to about 70% of the sun's output. But what does happen is that 30% of the sun's output gets reflected by the Earth's atmosphere and surface. This narrow arrow here is reflected to space, and that's why it remains shortwave radiation. Then you've got quite a substantial amount of the sun's radiation being reflected to space. And then what we have is aerosols, which are floating around in the air that also reflect some of the heat back to space. So for the sun's solar radiation is 100%, but 30% of it is reflected to space, and that is known as the Earth's albedo. Now, the Earth has to stay in balance. The heat that the Earth absorbs must equal, absorbs and reflects, must equal what the sun, what is radiated from the Earth. If that doesn't happen, the Earth either gets warmer or it gets colder. And I've shown it here. First of all, the clouds themselves can radiate to space. So you get long, and they radiate at a completely different frequency to the sun, long wave radiation. So when you're doing measurements of radiation measurements, it's not difficult to tell whether the radiation originates from the sun or from the Earth because they're at different frequencies. Some of the heat that the Earth absorbs can escape directly to space without any resistance to it reaching space. And that's known as the atmospheric window. And then you have the bulk of it, which is transported to space via greenhouse gases. And the way the greenhouse gases work is that near the Earth's surface, they absorb the radiation from the ground very quickly. Within the first 10 meters, that radiation is is absorbed, but it then has to be transferred through the atmosphere and radiate out to space. And water vapor is the major player, and it radiates most of its energy to space from the troposphere. But carbon dioxide, which is also a fairly important gas, radiates both from the troposphere and from the stratosphere. And I'll talk about that a little bit more later on. But you can see there are actually two levels at which carbon dioxide radiates to space. And that's to do with the quantum mechanical aspects of water vapor and why it radiates at different frequencies. Now, the important point here, I've drawn it at the top here, the total outgoing energy has to equal the total incoming energy. That's an absolutely fundamental principle. However, of course, if you put more greenhouse gases into the atmosphere, you can slow down the rate at which it goes, the heat goes to space. And the only way that the Earth could then stay in balance would be for the surface to get warmer, because it must put out what's coming in. Okay. Now, if I was to go up and have a look at the top of the atmosphere, and that's at about an altitude of 100 kilometers, at a planet like ours, without greenhouse gases, we would get a radiation which closely approximates that of a black body at 288.7 degrees Kelvin. And the spectrum that you get is known as the Planck spectrum. Now, the significance of that is that the area under a plot of spectral flux versus wave number is equal to the total energy radiated by a black body, which I'll call Q watts per square meter. Now, the Q can be computed from the Stefan-Boltzmann equation, which is the one in the next line here, where Q is equal to epsilon sigma T to the power fourth, to the fourth power, where E is the emissivity of a body, and for a black body, it's 1, and sigma equals the Stefan-Boltzmann constant. So I can work out, when it's a black body, you don't need to calculate the area under the curve. You can do it from that equation. However, when we look at greenhouse gases in the atmosphere, it's a little bit more difficult, as we'll see in a couple of slides. And note that T here is the absolute temperature, which is expressed by this little equation. 1 degree Kelvin is 1 degree centigrade plus 272.15. 0 degrees Kelvin is absolute zero. It's the minimum temperature that anything can reach. And here's the spectral flux that you might expect to get at a surface temperature of 288.7 degrees Kelvin with no greenhouse gases. This is taken at the top of the atmosphere, this is being representative of what you might see at the top of the atmosphere with no clouds, because if you bring clouds into the equation, you can't do the balance. So this is an ideal situation. I'm taking a clear sky. And this is at mid latitude. Obviously, if you were to do this down at the poles, the temperature would be considerably less than this, but this is a very good the basis to use for comparison purposes. So you'll see the blue curve here is the Planck spectrum, which was first described by Max Planck in the year 1900. And he was the father of quantum mechanics. He worked out how to compute the shape of this curve. And then using the Stefan-Boltzmann law, or working out the area under this blue curve, you get a number of 394 watts per square meter. So that would be, if we had no greenhouse gases on Earth, that's how much heat would be radiating to space at a mid latitude. Just a point here that you'll see I've got spectral flux on the vertical axis in watts per square meter per centimeter. But at the bottom, I've got wave numbers, which are reciprocal centimeters. And this is a convention that radiation physicists like to use rather than frequency, but you can convert from frequency to a wave number through this little formula that I've shown you. In other words, one reciprocal centimeter is equivalent to approximately 30 gigahertz. But don't worry about that. We start off down here with the frequency of 0, and as we get up here, the frequency gets greater and greater. All right. That's all good and well. What we really need to do is have a look and see what does it look like when you put greenhouse gases into the Earth's atmosphere. Of course, there are plenty of them at very low concentrations. So when we measure the actual distribution at about 100 kilometers above the Earth's surface, you don't get a smooth curve like the Planck curve that I've just shown you, but you get a jagged curve. And this is known as the Schwarzschild curve, a spectrum named after the German physicist Carl Schwarzschild, who was the first physicist to work out how you might determine what such a spectrum would look like. I will add, back in his day when he did this, he could do the theoretical side, but there was no way of measuring it. We've only been able to measure the spectrum for a little bit over 50 or 60 years. So the jagged shape comes from the greenhouse gases. Now, the one thing we should note is that were there no greenhouse gases on Earth, then the planet would be much colder than it is, and far too cold to sustain life as we currently know it. And carbon dioxide has one advantage: it also helps to moderate the day-night temperature swings. We don't freeze to death at night because we've got greenhouse gases keeping us warm, plus the retention of the heat of the planet itself. So it's a mixture of the two. This is what that curve looks like, the actual spectral flux measured at the top of the atmosphere. This is with greenhouse gases. And you'll notice here that the area under the curve has dropped to 277 watts per square meter. So with no greenhouse gases, it would be 394, but with greenhouse gases at a temperature of 288.7, the radiation would drop to 277. That's quite a big difference. And as I said earlier on, the heat that the Earth receives must be re-radiated. And the only way the Earth can do that, if you're going to lose if your radiation, the rate of heat loss to space decreases from 394 to 277, is for the Earth's surface to heat and compensate for that. But I've shown you what the curve really looks like, plus all the different greenhouse gases, where they affect the shape. So from that smooth curve, we've gone to this jagged curve, and you can see quite a big chunk of the smooth curve over here has been taken out by carbon dioxide. The other big one is water vapor. Now, it becomes a little bit complicated showing water vapor and carbon dioxide on the same diagram because their absorption and emission lines overlap, so you can't always tell which is which. But they are actually the main ones. But all of the greenhouse gases have some effect on the shape of this curve. And here I show you the two curves compared to one another in one slide. The blue curve here is the Planck spectrum, and the black curve is the Schwarzschild spectrum. And the difference between these two curves, the green shaded area on this chart, is the greenhouse effect. This is effectively what it is. And the area in this, the area of the green area is equal to about 117 watts per square meter. That's how much greenhouse gases are reducing the radiation going out to space. Now, the point to remember is that greenhouse gases emit heat to space not from the ground, but from much higher altitudes. And at higher altitudes, temperatures are lower unless you get right up into the stratosphere where the temperatures start to go up again. But what this is effectively doing, this change in radiation to space, is changing the Earth's emissivity. And if you remember from the equation I showed you earlier on, the heat radiated to space is proportional to the emissivity times the Boltzmann's constant times the temperature to the power of 4. So we drop the emissivity of the Earth for an ideal Planck body from 1 to 0.7. It's reduced by 30%. Okay, so what dominates the greenhouse effect? Water vapor dominates the effect, accounting for most of the difference between the two curves. An important point to remember here, its concentration is set by the sun-driven ocean heating, which warms the seas, which gives more evaporation and higher vapor pressure. Many people mistakenly think it's the warm air that warms the seas. The air simply hasn't got the heat capacity to make any measurable difference to sea temperatures. Sea is heated by the sun and pretty much the sun only. Obviously, there are volcanoes and other things under the sea that can warm it as well. But as far as radiant heating is concerned, it's principally from the sun. CO2 contributes a minor share of the natural greenhouse effect, depending on the overlap with water vapor. So CO2's direct planetary temperature regulation is at best modest. If you add in clouds, then water vapor share can exceed 90%, and the effect of carbon dioxide is reduced to less than 10%. So you can see the picture that is building up here. The dominant greenhouse gas on our planet by far is water vapor. Water vapor in the form of water vapor, and in clouds. I'm not covering clouds in this presentation, but that in itself is a subject on its own. Okay, but let's not completely poo-poo carbon dioxide. It obviously is affecting the planet, and we humans are continuously adding more and more carbon dioxide to the atmosphere. And the key question we need to answer is, does raising carbon dioxide noticeably alter Earth's energy balance? And to answer this, what we do is we going to do a climate sensitivity to CO2. And what I'll do is we'll look at what happens to the change in radiation to space if we double the concentration of carbon dioxide. Now, as we stand today, it's somewhere between 425 and 430 parts per million. So we're going to look at what happens if we double it. In fact, the exercise I use is from 400 to 800 parts per million. Okay, and what you're going to find is that the change in radiation from doubling carbon dioxide is actually surprisingly small. It's only a few watts per square meter. Here's the way that you do it. The blue line here again is the Planck spectrum. The black line is the solid black line is what the radiation spectrum measured from the top of the atmosphere would look like, with 400 parts per million of water. But then you can see superimposed on top of that is a dotted line. I've shown a bit there. You can see a bit of the dot there. For pretty much all of this curve, the dotted line coincides with the solid black line, but there is a difference. And what happens is at 400 parts per million carbon dioxide, the radiation to space would be 277 watts per square meter. If we then doubled it to 800 parts per million, we would reduce the radiation to space to 274 watts per square meter. And all that does is change the flux by 3 watts per square meter, which is of the order of 1%. So 100% increase in carbon dioxide only gives a 1% reduction in radiation to space. Okay, so what does this mean? Well, this equates to about a 0.7 degrees centigrade surface warming with no feedbacks. Why does the surface have to warm? Because it has to balance the heat coming into the planet. So if you increase the resistance or you decrease the emissivity of the Earth, you have to increase the surface of the Earth in order to make sure that all the heat escapes. Now, something that is very poorly understood and not well known is that the carbon dioxide is tending towards saturation very, very rapidly as concentrations rise. Let me just expand on that a little bit. So the situation is that for each doubling of carbon dioxide, you only get 3 watts per square meter added resistance to the heat flowing to space. So if you go from 400 to 800, it's 3 watts. If you go from 800 to 1600, it's 3 watts. And if you go from 1600 to 3200, it's also 3 watts. So you can see it's getting progressively less and less. I've got a chart here which I've put in to put at ease some minds who might say, well, where do I get these charts from? How do I know that what I've shown you so far is accurate or not? And we can't measure the Planck spectrum. We calculate that because they're greenhouse gases. We can measure the actual spectrum with greenhouse gases, but we can't measure a spectrum with double greenhouse gases. We have to go back to absolutely first principles to do it. It involves a lot of mathematics, but it can all be solved on a laptop. So what I've done here is I've looked at the models. Models have been developed by Professor Happer at Princeton University, and there are 3 models that I'm going to show you here. There's what the radiation would look like according to his model in the Sahara, in the Mediterranean, and in the Antarctica. On the right, I've plotted the graphs of the actual measurements. And if you look at the graphs in the left-hand column compared to the right-hand column, you can see they look almost identical. The likeness is absolutely remarkable. Just bear in mind that each of these are on a different scale. In the Antarctic, our vertical axis is from 0 to 60, whereas in the tropics, it's from 0 to 200. And obviously, much more heat radiates to space in the tropics than it does in the Antarctic. And the middle chart here is the Mediterranean model, which is the one that I've just been. It's the area where we've been looking at so far. Ours goes down to 0 on the horizontal axis. These ones only go to 400. But there's something very interesting to note in these charts, and that is that in the Antarctic, the actual emission curve sits above the Planck curve, not below it like it does in the Mediterranean or the Sahara. And the reason there is that the air above the Antarctic is much warmer than the air above the ground. And down in the Antarctic, the carbon dioxide actually amplifies the cooling of the Earth. It doesn't cause any heating. It actually causes cooling in the Antarctic regions. Okay. To further support what I'm saying is I took the Mediterranean model, the Sahara model, and I asked ChatGPT to digitize the measured curve. And I then said, well, let's plot the measured curve next to the theoretical one. So now you're not looking at the two charts separately. They're on top of each other. They are imperceptibly different. There are small differences. Could be modeling imperfections, probably more likely to be measurement imperfections. But when you come to environmental modeling, if you get something that is as accurate as this, you can rest assured that the methodology that you've used to arrive at these curves is pretty sound. Where I am now is the blue line. That's the measured curve, there where the pointer is, and that is the modeled curve. Now, at 430 parts per million carbon dioxide, which is just about where we are today, most of the heat absorption is already complete. Increasing carbon dioxide concentrations raises its emission altitude. So what happens is, as the concentration of carbon dioxide increases, the point at which it radiates to space, the emission height rises through the atmosphere, goes up to a higher atmosphere level. So those emissions which are happening by carbon dioxide in the troposphere go up to a higher level where the temperatures are lower. Now, where the temperature is lower, the radiation intensity is less. So that would lead to less heat being radiated to space, and consequently, the surface would need to warm to compensate for it. But what is often also not understood, carbon dioxide also radiates in the stratosphere. In fact, the strongest absorption band is in the stratosphere. And as the emission height in the stratosphere increases, if you remember the chart of temperature versus altitude in the stratosphere, the temperature is going up. So as you go up in the stratosphere, the radiating temperature goes up, and therefore the radiation quantity goes up. And these two are virtually in balance, which is why you're only getting that 3 watts per square meter change for a doubling of CO2. Okay, so that's basically a slightly closer look at what the physics is doing. Another way to look at it is to look at what would happen if I took a big barn and I painted it red. Let's supposing I equated the first coat of red paint to 400 parts per million of carbon dioxide and called that the first coat. If I then wanted to go to 800 parts per million, I put on a second coat, because now I've got 2 coats, each with the same thickness. And what you notice is that the barn maybe is a tad redder. I certainly can't see the difference in these 2 photos, but maybe the one at the bottom is a bit redder than the top. But you can see there's hardly any difference. And adding a third or a fourth or a fifth coat of red will make absolutely no difference. And that is what's happening to pretty much all the greenhouse gases. They've reached a level at which increasing their concentration doesn't increase their effect on planetary temperatures any longer. Here's another way of looking at it. This is a chart of global warming for each additional 50 parts per million by volume of carbon dioxide. And if you plot incremental warming on the vertical axis in increments of 0.2, and concentration of carbon dioxide on the horizontal axis, you will see that at very, very low concentrations of carbon dioxide, if you double your concentration from 100 to 150, you make quite a big difference in the temperature. But as you go further and further along the curve, as you keep adding 50 parts per million of carbon dioxide, you make almost no temperature difference. If we look where we are today, which is where this red arrow is, and where we would be when if we doubled it, the change in temperature is, well, it's going down by progressively smaller and smaller and smaller amounts. And the difference eventually is only about 0.7 degrees centigrade. What is often not appreciated as well is just how vital carbon dioxide is to life on Earth. If we were to take concentrations down below 150 parts per million, where this line is, what would happen is plant life would cease to exist. And without plants, there's no foodstuff for animals. So we would all cease to exist. So you can't, there is no such, there's no ideal with no oxygen, carbon dioxide in the atmosphere. It's an absolute must. It's a fertilizer. It's essential for plant growth. Reference is often made to the pre-industrial period, which is around 200 years ago, where concentrations were at about 180 parts per million, not an awful lot above the minimum survivable quantity of 150. And here we can see where we are today. But what you can see from this chart is that per additional 50 millimeters of 50 parts per million of carbon dioxide, you get a very, very small increase in temperature, and it tends ultimately to zero. This is actually a log 2 plot that you can see here. So this chart clearly demonstrates that carbon dioxide has a logarithmically diminishing effect, strongest at very low concentrations and much weaker at higher levels. If you took it down to extremes and you went down to the first part per million of carbon dioxide, near to zero, and you added 1 part per million, if you went it from 0 parts per million to 1 part per million, then the effect on the heating of the planet is 1,000 times greater than adding 1 ppm is today. And I think this is where some physicists get mixed up, is they might be aware that at very low concentrations, there's a very steep greenhouse effect. But as you get to the levels we've got today, the effect becomes saturated, and adding more makes very little difference. The doubling of today's CO2 levels can only lead to an increase of 1 degree centigrade with a forcing of about 3 watts per square meter. This is without any feedbacks. So what I'm basically saying in a nutshell, if you double your concentration, in other words, increase it by 100%, and you will reduce the radiation to space, you call it the radiative forcing, by 3 watts, which is 1%, and that will give you a rise of about 1 degree centigrade, which is only 0.25% of the temperature. So the effect is very, very small, even though you've doubled the amount of carbon dioxide. So clearly, carbon dioxide is not the Earth's temperature control knob. It has become far too weak a greenhouse gas to have any meaningful effect. What does this mean in terms of net zero? Because remember, our policies of net zero are designed to avert any further warming of the planet. Now, you can, using the same methodologies that we use to work out those curves that I showed you earlier on, we can work out what achieving net zero between now and 2050 would lead to about a 0.07 degrees global temperature reduction. And if I consider continents like the USA, the net zero contribution would be less than 0.01 degrees centigrade. And for the UK, it would be an unmeasurable 0.001 degrees centigrade. And this is because of the logarithmic effect of what's happening, and because it is pretty much a saturated phenomenon. Just let that soak in a bit. Those are tiny, tiny, tiny numbers. So if we did nothing, the Earth's temperature could warm by 1 degree. It would take us until the year 2200 for the concentration to double. That's the end of next century, not this century, until the end of the next century. Bear in mind, and as I said, I haven't covered the physics of clouds, but all it takes is a 1% change in cloud cover to change the outgoing radiation by 3 watts per square meter. So if you ask yourself, well, what is having the biggest effect on Earth's temperature? It's quite clearly the clouds. There are other long-term effects. The output of the sun obviously changes with time, and the oceans affect it, but those are over very much longer time spans. Clouds can change by 3 watts per square meter in a matter of minutes or hours. If you watch how clouds can change above you on a cloudy day. So I'm afraid, Nate, it's natural variability, which is far outweighing weighing any human carbon dioxide emissions. Okay, I just want to quote this. At the start, I said everything should be made as simple as possible, but not simpler. And I've tried to follow it here. I hope I've achieved it by showing you the essential physics of greenhouse gases without drowning you in equations, but also without reducing it to slogans. The key message is that water vapor and clouds dominate, while extra CO2 adds only a modest diminishing effect. The physics is plain, is as simple as possible, and no simpler. Yeah, just a closing comment. Water vapor and clouds dominate the greenhouse effect. Extra CO2 adds only a modest diminishing effect, and the physics is as simple as possible. No simpler. That's what's happening. Thank you.
I'd just like to compliment you on presenting that very clearly. That was really nicely done. So thank you for doing that. So then I would like to ask, you have delivered something like this in public recently. I'm curious as to how it went over and what sort of questions you got afterwards.
It's funny, Tom. I live in a country which is a lot more skeptical than the States about, not skeptical, lot more alarmist than in the USA. I have had, to be honest, I've had no serious pushback. You kind of get almost a stunned silence. The skeptical community will come along with you and say, yes, we agree at all that. What I'm really trying to do is to get people to understand what's really going on. And it's not, look, who wouldn't want to live in a better environment? But by believing that you can do something positive by changing carbon dioxide, you're making a big mistake. And an expensive mistake, a very expensive mistake. I mean, I'm a chemical engineer, as you know, and it doesn't make sense at all. But it comes as complete news. I couldn't find a single textbook to go to for this material. I had to go. I have to say the CO2 Coalition is an excellent resource, but even then, you've got to have a pretty good grounding in physics to understand. If you want to understand HAPA's work, you need to know, what it is that he's doing. How do we get this across? it's very difficult, Tom. But I'm glad you think it's not been too complicated.
So are you okay with mentioning that you have worked with Will Happer, or you've been in his office, and he encouraged you to do this on this podcast, right?
Absolutely, yeah. I get on very well with him. The guy is a quiet genius, and that's all I can say. He has an unbelievable knowledge of what goes on in physics. When you talk to him, you realize you're talking to a grandmaster. I've tried to encourage him to write a book, but he's not interested. But I wish somebody would take something like this and develop it into something that is more widely available. That I think would help a lot in trying to get the message across. I'm looking at it purely from a scientific point of view, Tom. I'm not interested in the politics. I couldn't care less. I've got lots of friends who are from the left and they don't want to accept it. Well, that's their business. As far as I'm concerned, the science is settled. Yeah. And the science is carbon dioxide doesn't make a meaningful difference. And that's what convinced me. At first I heard, all the, it was really through COVID where it was really heating up this whole environmental debate. And I just said, I can't believe this. But it was only once I got to master the physics that I realized, yes, somehow or other a false narrative has got out. And I don't know how it's happened. You never have a journalist querying anything that he's told about the environment. They never, ever query it. But if the physics doesn't support it, it doesn't matter what, if you go back in history, you can see carbon dioxide's been higher, been less. The Earth has been warmer, it's been colder. But so what? If the physics doesn't support it, there's no correlation between the two.
So one other question is that it says no feedbacks a couple times in your presentation. I think that it gets beyond the realm of physics, right? To figure out in the real world, if you do double CO2 and leave everything else the same, because you've got increased plant growth and you have maybe the winter gatekeeper where the heat's moving around and escaping through the poles. Do you have ideas on the real number in the real world with feedbacks?
You know what? Again, this is from my chemical engineering experience. Natural systems have negative feedbacks. The net feedback is negative. Tom, if it wasn't, the Earth would be very unstable and we wouldn't be here. I think few people understand it. It doesn't matter if it's positive to any degree, then the planet's finished. Because let's supposing you go out and have a barbecue, you're going to warm the air a little bit. There's going to be a positive feedback because of that. And that's going to lead to another positive feedback and another one and another one. I mean, what's going to stop it getting warmer if you've got positive feedback? So it's not natural to have positive feedbacks. The best example of a positive feedback is an explosion, because there you want it to feedback positively, but that's what happens. There are lots of negative feedback mechanisms and there are lots of positive feedback mechanisms. I mean, you could even argue, I suppose, the greening of the Earth is going to, reduce the albedo. So, that would lead to warming of the Earth. But the big one is clouds, and we have absolutely no idea how to model those clouds and how. Yes, if you warm the oceans a little bit, there'll be a little bit more water vapor in the air. And yes, that could make it warmer, but depends. If it forms more clouds, it'll make the planet cooler. And I'm pretty sure that's what's happening, that the clouds are adapting as best they can. This is not like a man-made control system where you have a set point and you have a controller and you have a variable that you can alter. But that must be nature's way of doing the best it can with what it's got. It can't control carbon dioxide and it can't control the sun, but it can control the clouds. There's also what you call the Planck feedback. As the Earth gets warmer, the shape of the Planck curve changes, and so that the atmospheric window allows more heat out. But you're getting into all sorts of complicated things. The interesting thing is that we're always predicting that it's going to get a lot warmer and worse because nobody can measure the future. So where does the story come from? And at the moment, the Earth is benefiting from being warmer. I don't think anybody's really thought about what would happen if it started going cooler again.
Yeah, I mean, the Little Ice Age, of course, was a tough time for life on Earth, of course. So, yeah.
Of course, yes. And it could turn at any time. Something else I keep repeating to people is that in 1 year, when the Earth orbits the sun, because it's an elliptical orbit, the sun's radiation changes by 90 watts per square meter over a year. Okay, that's a lot. I mean, doubling CO2 only adds 3. This is 90 in 1 year. And yet the temperatures between the sun, the Earth being close to the sun and further from the sun are maybe 1 or 2 degrees. So the feedback mechanisms and that exist are working. It must be. Otherwise, we surely would see a much bigger swing in temperatures from winter to summer, depending on which part of the planet you are. We're nearest the sun in the northern hemisphere in summer, I think, and furthest from in our winter. But I don't know, or the other way. I can't remember where the perihelion and aphelion of the orbit around the sun is. Do you know? I just can't remember that.
I don't. I think it's counterintuitive about when Earth is warm. I forget. But
it's a huge 90 watts per square meter, though.
I can already tell that I would like to have you come back and do your photosynthesis talk a little later if you want to do that here.
Yeah. Okay. It's nearly finished. I'm just adding a few polishing touches to it. I'm going to talk about the different photosynthetic cycles and how plants have adapted to different levels of carbon dioxide and et cetera, et cetera. Yeah, that would be great. I'll let you know when it's ready.
Perfect. All right. Any other points you want to make before we finish up this one here?
I think if, for example, a U3A group in the UK happens to see this and would like to have the presentation, I'm willing to travel most parts of the country. If anybody in the States, I go to New York a few times a year because I've got a son that lives there. Quite happy to talk to people. Schools would be the ideal. If I could speak to A-level students, students who are doing physics for their final year at school, this would, I think, add a lot. I've got one that's more advanced. It's twice the length of this, where I go into the why greenhouse gases are greenhouse gases. That I didn't cover today. That's another fascinating topic, is, what's the reason that they absorb any heat at all? But that's the kind of thing you can also give to school children in their final year.
So that's a talk you have already ready to go?
Yes, I have it already.
Okay.
But a lot of this overlaps with that. I gave it a 2-lecture series earlier on, and it's a bit more technical, but if one day you'd like to look at that, I can show that to you as well.
Yeah, let's look into that. I think that could be good for this channel too. All right. Yeah. Okay, I think that's it for now, but thanks a lot for what you're doing. I appreciate it, and I'm looking forward to having you on again.
Well, it's a pleasure being on, and keep up your good work, Tom. We've seen there's a marginal shift in the UK to a less alarmist position. The official opposition announced this weekend that they're going to drop net zero, which is quite good. The strongest party in the polls at the moment has said they're going to drop net zero. But I just a word of caution there. They are dropping it because they can see what financial damage net zero is doing. But none of them understand why we shouldn't be doing net zero, that it's a pointless exercise. Because it doesn't matter whether you have floods or droughts or anything. It's not caused by carbon dioxide. So get on with your life and do the right things. Prepare for it,
I 100% agree.
Yeah.
Okay. All right.
Okay.
I'll let you go, but thanks again, Rob Louw. Talk to you later.
It's a pleasure.
Bye.